Newell Award. And in 2023, he founded the ELLIS Institute in Tübingen, where he acts as its scientific director. But obviously, more than the long list of accolades, Bernhard is an absolute titan in our field and known for his pioneering work on support vector machines, kernel methods, and causality that has left a lasting mark on the work that we all do here. So I'll turn it over to you, Bernhard.
Thank you very much. Yeah. Can you hear me in the back? I will try to speak up. Please give me signals. I'm not very good at this kind of acoustics. Yeah, thank you very much. It's very nice to be back in the Vector Institute, because without the Vector Institute, the ELLIS Institute also wouldn't exist. Without CIFAR, it wouldn't exist, but also specifically Vector at some point. I remember I was asked to join a trip of some German politicians, and they wanted to visit the Vector Institute, and they asked me to come along, and then we got to meet Jeff and Rich and others, and then the politicians said, we want something like this also. So you guys got me into a lot of trouble. So anyway, yes, now I'm here. And I have to apologize already. I'm a little jet lagged. I arrived yesterday to New York, but then I woke up at 2 or 3 in the morning, and I thought I watch a bit of TV in the hotel room. That would put me to sleep, but I turned it on and I really saw a speech where someone was celebrating. I was sleepy. I don't even quite remember, but something was the greatest in history. I don't quite remember what, maybe I don't want to know. But so let's see. I'll try to do my best. So I'll start. So it will be not very technical. It's more about the thinking of our work over the last 10 years and maybe also the next 10 years, I imagine. What's been driving it and what are some of the main ideas behind it, with a little bit of technical things interspersed into it. So a little bit of history. So 1958, bring up my volume. This is a page from the New York Times, where they're discussing this new machine called the perceptron. And this is Frank Rodenbach, who demonstrated the perceptron. It was a physical machine. And he said that this machine is the first to think like the human brain, to learn from experience. And he speculated that later perceptrons will be able to recognize people and translate speech from one language to another one. And I bet nobody believed him at the time, because what he did show was ridiculously simple compared to that. Oh, that's great. That's great. It is better. Huh? Yeah. You haven't missed much yet. So, but we've come a long way, and I think one example was this recent Nobel Prize that went to Jeff Eaton, that showed that not just have we come a long way in AI when it comes to modeling intelligence, but also we've come a long way in that natural sciences are being transformed. Otherwise, he wouldn't have gotten the Nobel Prize for physics. And I think maybe this is, let's see how we think back in 10, 20 years to the days now, whether we will say the main impact of AI was it has changed how we build intelligent systems, or whether we will say AI has helped us solve some major problems of humankind, or AI has transformed how how model building in the sciences works. So let's see, and it's of course also up to us how people will look back at AI, especially whether they will see it as a positive thing. So it's in our hands, I think. So this is another interesting development that happened. So this perceptron was kind of the starting point of machine learning, of neural networks. And around the same time, another revolutionary development took place, and this is that people understood that computers could do more than compute with numbers. So originally, a computer was a job description. They were humans, typically women, who were sitting there doing calculations. That was a computer, and nowadays it's a machine, of course. And around in the 50s, people understood that these machines can compute not just with numbers, but with symbols. And this was really, in hindsight, probably the birth of computer science, and quite a powerful paradigm shift. And so effective that people thought for quite a while that manipulations of symbols is actually enough to generate intelligence. So manipulation of symbols, according to programs written by humans. So people seriously believe that this is all there is to intelligence. And we all know by now that this has failed. And I think a nice picture to illustrate how this has failed is this one. So this is, I think, the match when Deep Blue beat Garry Kasparov in chess. So at the beginning, people thought, once we can beat a world champion in chess, surely we must have reached intelligence the same level as a human, because that's the most complicated thing that humans do, or one of the most complicated things. And then they beat him. But the surprising thing in this picture is that if you look at Deep Blue, it seems to be that Deep Blue is a human. And the reason is that Deep Blue was very clever playing chess, but Deep Blue couldn't recognize chess pieces or move chess pieces. So, so computers were surprisingly good at things that looked hard and surprisingly bad at things that looked simple. And this has become known as Moravec's paradox. So, of course, now things have moved. And of course, we believe they have moved because of machine learning. So I'll show you just two brief examples from my lab. This is one example where we use machine learning to train a system that's hard to control. It's a pneumatic robot inspired by human muscular systems that learns to play table tennis. And here's the second example that I quite like. This is from the field of gravitational wave inference. So you probably heard about these gravitational waves emanating from black hole mergers, so black hole merger. So this is a computer visualization, how the thing supposedly would have looked from a nearby observer. So what you see, okay, the black holes, you can't look into them, but you see that they distort the light around them. And so normally if two things orbit each other, it can go on for a long time. I mean, our planet has been orbiting the sun for billions of years, and we hope that it will continue for a while. But if you have two black holes, what is this? I don't know. If you have two black holes, if they get close to each other, they're very heavy, they can move very fast. So just before the merger, they move around hundreds of times per second. So imagine you have two things that are both heavier than the sun, and they move with a frequency of more than 100 Hertz. So that's a very dramatic thing. And then the gravitational waves that get emitted are significant. And this means that they lose energy as they rotate. And if they lose energy, it means the orbit is getting lower, and eventually they will merge. And then the first, I don't know, it doesn't show on my screen, this thing. I can try to click. Maybe I should give the talk in French.
Oh, what's going on? There we go.
Okay. Where did I stop? So this is the first time they measured something like this. Was still during an engineering test run of the LIGO observatory. The observatory consists of certain interferometric apparatus, which is several kilometers long in different directions. And then they measure, they have laser light going back and forth, and they measure slight changes of the length of this, because space-time itself deforms for a gravitational wave. And the shifts are on the order of the diameter of the nucleus of an atom. So it's tiny, over several kilometers. So it's quite amazing that this actually works. And then first event they measured during the engineering run, it was so large that they could have measured it no matter where it had taken place in the universe. So it's maybe the most extreme event that you can imagine. And then the amazing thing is that from that, you can estimate a number of parameters of these events. So black holes don't have a lot of parameters. And there's something called the no-hair theorem. So black holes don't have hairs. They are, in steady state, they're fully characterized by just, I don't know, position, angular momentum, mass, and charge. And charge is irrelevant on a scale of a black hole. So there's still, I don't know if you have two things merging each other, there's something like 20 to 25 parameters to this event, and then you can try to estimate them from these tiny deformations of space. And they were doing this with Monte Carlo methods, and so this was a project that we did together with those guys, where we used machine learning methods, normalizing flows, to estimate the posterior distribution over these physical parameters from the deformations of the space. and to estimate them very fast, because that's it's important, especially as you're moving, which is what we're doing now, to the merger not of black holes but of neutron stars, which are just a little bit less heavy than black holes. Then there's also interesting things to pick up in the electromagnetic spectrum, so light. But in order to pick that up, you have to know where it happens. So once you notice something is happening, you have to be able to point your telescope there. So you can't take one day to run Markov chains before you can decide with the telescope. So machine learning is great. We all believe in that. But I want to talk a bit more about the shortcomings of machine learning to motivate why I'm interested in causality. And this is one beautiful example, but there are many of the same type. So an old one that motivated a lot of our work at the time was what has been known as the urban tank, so the tank urban legend. But I prefer to have non-military example of this. So this is an example where people collect radiographs of patients and healthy people to detect pneumothorax, which means partial lung collapses. And you can see this in the X-ray. So I think this person has a pneumothorax over here. So they did very well with neural networks, but then when they applied the system to a new patient coming in, they noticed it didn't work. And the reason for this, when they started analyzing, trying to work out where's the neural network looking, and then they notice it's looking over here, and you see a little thing here, which is a tube that the doctors insert if you have a pneumothorax. So the system didn't really learn to detect the pneumothorax. It learned to detect this signal that the doctor applies once you have a pneumothorax. So for new patients, it was completely useless. And that's an interesting example. It already feels it has something to do with causality, it has something to do with distribution shift. And in the talk, I'm just going to try to argue that this is sort of two sides of the same coin, it's more or less the same thing. So why are we interested in machine learning, or what kind of properties would we like the system to have? And I should say maybe this goes a little bit against the current mainstream. We think we're just going to kill everything with more data. And who knows? I mean, that's the beta lesson. Maybe the beta lesson will continue to be true. But in a way, I like to think that the field would be less boring. It's not true. So we have to try to see, can we somehow make it not true? And so what kind of properties should systems have if data is not going to solve everything for us? And certainly, I think for humans and animals, not everything is solved by data because we have constrained resources. Our heads cannot grow much bigger, otherwise the birth process wouldn't work anymore. So we have to reuse things, we have to transfer things. So we need support for our distribution generalization. And so the IID assumption has been called the BBVA of machine learning. We need support for multi-environment problems, multi-tasks, fast adaptation, lifelong learning. We also need systems that are interventional in the sense that they allow planning, explanation, credit attribution. And there's another thing that we have in analogy to OOD, we've called it out of variables. I'll talk a little bit about that. This is about this assumption. We're not only assuming that the distributions don't change during learning, but we're also typically assuming that we always see all variables. And it might be that you see completely different variables during training and testing, or maybe even between different training runs that you're observing different things, and you have to somehow put it together to build a system that will work on a test set. And then at the end, a few thoughts. Maybe I will get to this also about trainability and communication, cultural learning. But I think I will have to see some things, and I don't get worried when you see this number. So, but I will at least tell you some of the basic ideas, and then we'll see how it goes. So this is Leibniz's principle. Leibniz was really the first person to understand the connection between causality and statistics. And he said, let's imagine there are two variables. We have two observables that are correlated, so empirically correlated. So for instance, in some data sets in Europe, the frequency of storks and the human birth rate are correlated. Now, we all know correlation is not the same as causation. Of course, it could be the same, so it could be, in this case, one possible explanation is that the storks bring the babies, or maybe that the babies attract the storks. But Einbach was saying the generic explanation is that there's some variable that causes both of them, and this variable could coincide with one of the two observables. And then this variable could be something like economic development. It's a typical confounder. This is called a confounder. And now the interesting thing is, from empirical data alone, we cannot distinguish these three settings, but they behave very differently once we leave the IID setting. So as long as we're in IID world, everything is the same. We don't have to worry about it. But if we leave the IID setting, there are very big differences. In particular, with regard to the effect of interventions. So if we just learn a standard IID machine learning model, based on this correlation, it's not going to tell you how the human birth rate will react if we have more storks. And maybe slightly more subtly, it will also, a kind of intervention is also a sort of a natural shift going from one continent to another continent. Let's say you learn this in Europe, you want to apply it in North America. It would probably also not transfer in this kind of settings. So we have to worry a little bit more about causality as soon as we leave the IID world. And so this is a one slide summary about causal models, in case you haven't heard about them. The idea is, in the simplest case, without cycles, you have a directly cyclic graph. Each of the nodes has one observable, one random variable. And the arrows in the graph represent direct causation. And then direct causation means that a variable is a function of its parents in the graph. And so so function is deterministic. So far this is all deterministic. But then there's an unexplained, U stands for unexplained, noise variable. So at each node there's such a noise variable. And then the assumption is that all the noise variables are independent. Because if they were dependent, then we would go to Leibniz principle and say, actually, there's something else that causes both of them. So this assumption is called causal sufficiency. It kind of means that the graph that we are discussing is big enough to really model the non-trivial dependencies in the system. So the noise variables are independent. All the dependencies then come from the topology of the graph. So as this noise, this is where all the randomness comes from, as this noise spreads through the graph, according to these functions or these functional assignments, it picks up a footprint of the graph structure. It implies, and the distribution over these independent variables implies an observational distribution over all the x variables. And it has some non-trivial properties, namely as specified or as characterized by a so-called causal Markov condition. It turns out that due to the structure of the graph, you start with independent noises, then you get certain conditional independent properties in the graph. The condition on the parents, each variable, when conditioned on its parents, is independent of its non-descendants. So these are the descendants, the non-descendants is everything else apart from the descendants and the parents. And so this is nice, and that means in particular, there are statistically observable consequences of certain aspects of causal structure. All aspects that can be characterized in terms of conditional independence statements. Now, conditional independence statements, they always need at least three variables. It's a ternary concept, conditional independence. So if you only have two variables, then you're stuffed. You can't do anything with this. And I'll get back to that in a second. But maybe at this point, it's also interesting to note this model is coupled to the environment in two ways. One is through this notion of noises, independent noises. They are sort of the unmodeled influences of the environment. And the second one is these models, they come with the notion of intervention. And intervention here means that we change the mechanism. So if we change one of these functions, for instance, we could set one of the functions to a constant, means we clamp one variable to a constant value, and then we just go through the rest again. We compute the observational distribution simply by applying these formulas on cycles. So this leads to a unique solution, no matter where we intervene. So these are the two ways you could say this interacts with the environment. Now, I said it needs three variables. So when we started thinking about causality, we were quite intrigued. We were saying it's strange that there's nothing you can do for two variables because it feels like you should first understand what's going on for two variables. And we thought we had some toy examples where we thought it does make sense. We should be able to do it for two variables. And we wrote down an assumption which we call the independent causal mechanism assumption. And I want to show it with this example here, which is so-called a Boucher chair. So you can see it's not really a chair, it's these two separate objects. But if you look through this hole here, then it appears to be a chair. So that means if you look through this hole, then perception fails, because perception shows you something that's not there in the world. You see it in a chair. And why does perception usually not fail? In this case, we would say it does not fail because normally the independent causal mechanism principle holds true. So the principle says that the generative process is composed of modules or mechanisms that don't inform or influence each other. So in this case, with a very simple model of the perceptual process here is you have so the objects in the world, let's say P of world, and then you have the perception process, which gives you the P of a certain percept given what's there in the world. And we posit that normally these two things are independent, but if you look through this hole, you violate that assumption because you look exactly from one direction, which depends very much on what's there in the world, because this direction is tuned to this object. So perception can't fail if you violate this assumption. Therefore, let's postulate that normally this assumption tends to hold true.
Just to double check, so the prior example you gave where we had like the scans, like the X-ray scans, and it was observed that the model is basically paying attention to the signal, that was the doctors like intubating or providing whatever. That would actually be also a violation of the independent causal mechanism principle assumption.
I think you could probably argue like that. Yeah. Okay, so and there's a lot. I'm not going to go through this, but whenever you come up with something, you start digging into history. Every good idea has been around many, many times before, and I just want to make sure to give credit here. Also, this idea has been around in many different forms in history, even going back to Herb Simon and even earlier in econometrics. There are some things that are related to this. And now, in our terms, now in this graphical model or called the graphical model framework, first of all, I should say, so there's an equivalent characterization, equivalent to this causal Markov prediction. There are three equivalent statements. One is the local causal Markov prediction. Second one is a global causal Markov prediction that uses something called deseparation. It turns out that if these local independencies hold true, they immediately imply a broader class of conditional independencies. And then the third characterization is that distributions, these kinds of distributions here, they allow a certain kind of factorization into conditionals, which we call causal conditionals. And there's one conditional for each of those local mechanisms. So the causal factorization says you can write the joint distribution as a product over these conditionals where each node is only conditioned on its parents. I think you probably know this from graphical models. Now, in principle, of course, you could write the same distribution in many other different ways in terms of conditionals. For instance, this would be a generic form, but this is not the causal one. So in this one, these things would not correspond to mechanisms, whereas here, each of these P's would correspond to one of those functions in this last picture. So these would be the things that you intervene upon, and maybe also arguably the things that would tend to change if something shifts in nature. Now then this independent causal mechanism principle would say, would imply that if we change one of them, if these are different mechanisms, if we change one of them, it doesn't change the other ones. So they would tend to remain invariant. There's no reason why they have to change if you change one other one. And also knowing one of them shouldn't tell you something about the other ones. And then related to that, we sometimes talk about what we call the sparse mechanism shift hypothesis, which you can think of as a generalization of the IID assumption or a relaxation. So if you say, I'm going to consider distributions of this form, so IID would mean nothing changes at all. And sparse mechanism shift would mean we allow a sparse or a small number of these mechanisms to change from situation to situation B. So that seems better than a completely arbitrary change. Question is, can we somehow exploit this? Okay, so one example what this could mean is independent causal mechanisms is the two-variable case. So now I'm going to argue that in the two-variable case, which normally cannot be solved with conditional independence, if we make this independence of mechanisms assumption, we could in principle imagine that it's solvable, or we can. And we make it very simple. We say we have two variables, and one of them causes the other, but we don't know which way around. Now we want to decide that. So now let's assume X is the cause and Y is the effect. And we even assume there's no noise, so it's just a deterministic relationship, and to make it symmetric, let's say the function is singular. So let's assume that the input distribution, now our assumption, what does it mean? It means the input distribution is independent of the conditional, so that the cause distribution is independent of the conditional of effect given cause. So that's the two-variable case. The mechanism is the conditional of effect given cause. Since there's no noise, this conditional is just a function. So that means knowing this function doesn't tell us anything, knowing this input, this density doesn't tell us anything about this mechanism and vice versa. So that's our assumption. Now, if we propagate this input density through this function, we get an output density, and then lo and behold, this output density does know something about the function, because wherever the function was flat, the output density is large. So if the independence holds true in the causal direction, it is violated in the anti-causal direction. And one can also mathematically analyze this. I'm not going to go through that, but we can prove for a certain kind of formalization of independence, if it holds true in the causal direction, it is strictly violated in the anti-causal direction. So this is, but I'll tell you later, we have a more recent formalization, which I like even more, or which it somehow covers something different also. But maybe before going into that, maybe I'll do this just briefly. Yeah. It's important to realize that, so this is a statistical model that I talked about before. Why is it statistical? It's because these unexplained terms are independent random variables. But you could, in principle, have a different notion of independence. So you could say, I'm not going to start with random variables, I'll start with bit strings. And then I have to think about what's the notion of independence of bit strings. And then I have a different computational model. And the question is, can it also model causality in some sense? Maybe the world is not fundamentally stochastic, we don't know. This is possible if you use algorithmic complexity or convolved complexity. Two bit strings are independent if the joint compression is not shorter than the sum of the individual compressions. And there's also notions of conditional independence, etc. And then there's a model of you can write down this kind of, they're called structural causal models. You can write them down without probability theory, but using convolved complexity. And then you have noises. These noises are bit strings. They include programs that run on Turing machines that take as inputs the output of the other computations, etc. And it turns out you can prove a causal Markov condition in terms of conditional algorithmic independence. And you also get something that corresponds to this factorization of the joint distribution. In this case, it's a summarization or an additive decomposition of the convolved complexity of the overall system. Now, why is this nice? It's because you can connect it to physics in an interesting way. And so here we have a model. Asymmetry is something quite interesting in physics because the fundamental physical equations are symmetric in time. Nevertheless, we have things like the thermodynamic arrow of time, which seems to suggest you cannot change forward and backwards. Entropy does not increase, it stays the same or it increases. And it turns out you can connect this to the assumption of independent causal mechanisms. And maybe I'll first give you an intuitive explanation. So there's this example in thermodynamics. And don't worry if you're not physicists. Imagine you have two gases, different, I don't know, you have oxygen and two chambers, you have a window, a door in between. Now you open the door, the two gases will start mixing, the particles go on both sides. And then afterwards you have a big mess, and they're not going to unmix by themselves because entropy does not decrease. But imagine if you could just freeze time at some point, and you turn around the momentum of each particle exactly. And then you run it again for the same time that you gave for mixing, and then it would unmix because microscopically the equations are reversible. Now, why does it unmix, or why is this not a contradiction? We would argue the reason why this is not a contradiction is because if you run it forward for a certain time and then you freeze each particle and turn them around, and then you run the dynamics from that starting point, you now have a starting point that very much is dependent on the dynamics because it is the starting point that you have achieved by running the dynamics forwards for a certain time. So now you are violating the assumption of independence of the starting point and the mechanism. And so therefore, if the assumption holds true that the initial starting point of the system and the dynamics are independent, then entropy should not decrease. And this, and we can prove this in terms of Kolmogorov complexity. So if you're willing to accept Kolmogorov complexity as a proxy for physical entropy, which some people do in physics, then you can actually prove that it's an implication of the independence of initial state and mechanism. So the second law of thermodynamics, or the arrow of time, is the implication of that. So now I mentioned before we have a more recent formalization, which I think is also quite interesting and not completely understood yet. So I think there's still a lot of interesting things one can do with this. And this is a certain connection to a theorem which is fundamental for Bayesians, the definite theorem. You probably know about this. So I'll briefly summarize it. So the definite theorem is about exchangeable data. So exchangeable basically means you have a sequence of random variables that's computationally invariant. Now, if you had IID data, they would be computationally invariant, but the other way around is not true. So exchangeable is a broader class. Exchangeable processes are a broader class than IID processes. But definitely proved that every exchangeable case, exchangeable sequence can be written as a mixture of conditionally independent IID processes. So you have these are IID processes, they're conditioned on some variable theta, and then you mix, and then why is this interesting for Bayesians? It's because it's this distribution over this latent variable that sort of decouples these things and makes them IID. That's what's called, or that's what Bayesians would call the prior, or that would correspond to the prior in Bayesian statistics. So really, if you see exchangeable data, you would say, no, it's actually IID data conditioned on some latent variable, and there's a prior of this latent variable. And it turns out you can generalize this to in an interesting way to a causal setting. And if you make an assumption that it corresponds to this ICM assumption, then it all sort of fits together and makes a lot of sense. So here, so the generalization works like this. The first one we make, so we have now pairs of random variables, x and y, and it's again, let's imagine x is the cause, y is the effect. And let's imagine these are exchangeable. So we pollute the position of the pairs. And then we make the ICM assumption that corresponds to x causing y. So ICM assumption means somehow the distribution over x should be independent of the distribution of y given x. Now, this is formalized like this here. So let's parse this. So this means, so this brackets n means all the integers from 1 to n. And so this means that if you already know, if you know all the inputs from 1 to n, then seeing one additional input will not give you additional information about the outputs that correspond to 1 through n. So somehow, roughly speaking, this is the same as saying getting additional information from the input distribution doesn't give you additional information about the condition of output given input. Only that it's somehow, here's more precise what it means to give additional information. It's just a standard statistical independence statement. And then when you prove that if this is true, then there are 2 latent variables, beta and psi, such that you can decompose the system like this. So now you have these 2 priors factorizing, and then this factorization corresponds to a joint factorization of a shared causal structure or invariant causal structure that corresponds to x causing y, because it's distribution of x and this is over y given x. So in the graph, it looks like this, x causing y, and here you have the 2 independent definitive parameters. And this is yeah, so why is the okay, a bit before I interpret, does it work? No. Hello? Oh, okay, it works. Before I interpret it, there's also a generalization to the multivariate case, to the case where you have non-trivial DAGs, so graphs with more than 2 variables, but let's not go into that. But what's important is that it turns out if you have the exchangeable case, but non-IID, which means that if these priors here, the priors over theta and psi are not just atomic, so they're not just point masses, but they are non-trivial, so different things are possible. Then, so it is, if they're point masses, then this degenerates to the IID case. But if they're not, which means in an environment case that you have non-trivial different environments which generate your data, and then it turns out that this generally contains more information, because you can then probably identify the causal structure from this kind of data. So you could, it's kind of a nice formalization of this intuition that, well, first intuition is if you can intervene in a system, of course you learn more about the causal structure than just by observing it. But it turns out observing a system from multiple environments is a bit like intervening, and this characterizes it. So we used to always want IID data for machine learning because it makes our life easy, but this shows that non-IID data actually generally contains more information than just IID data. And I think this is the future of causality research, or it's the past and the future. So we just have to find good ways of exploiting this in machine learning also. Now let's get a bit more practical and think about how causal structure helps machine learning. So I talked before about how causal models imply statistical models. I talked a bit about the way back from a statistical model. When can you go back to the causal model? 3 variables, you can sometimes do it. If you just have 2 variables, it's harder, or you need additional assumptions. But you could say, I don't really care about causality, but I do care about out distribution generalization. So I care about getting good performance, even if the distributions change. So that really means you care about how to get from one statistical model to another statistical model that might be in a different setting. So let's look at one practical transfer problem. So let's say you've learned a multivariate density, and now something shifts, and you don't know quite what shifts. So it shifts from density P1 to P2, and then very naive sort of theoreticians would say this is completely underspecified. What do you have to observe to learn P2? And then of course, the answer is, if you know nothing about what changed, you just have to observe everything. You just have to start from scratch again. But imagine you believe that there's a shared causal graph that generates both of them, and sparse mechanism shift applies. So it's not IID, but the change is limited since it's just a sparse change. But in this case, actually, the problem is much easier, because then there's a shared graph. You know there's a causal factorization in terms of conditionals of these variables given their parents. And then you really only have to update, you only have to observe the variables that appear in the conditionals that have changed. And that could be a very small number if it's a sparse shift. I mentioned before auto variable generalization. There's also this problem. What if you only ever observe marginals over subsets of variables? How can you put them together? This also is a non-trivial problem. It's called the marginal problem of statistics. In general, it's not uniquely solvable, but there are approaches, maximum entropy, etc., how to do it. But if you can make causal assumptions about the graph, etc., then actually it turns out that you can specify more accurately. And I'm not going to go into detail, but we also have a recent paper that looks at one specific non-trivial special case and goes through that and shows how you can do something surprising just from observing the marginals. So now I want to, I think I put it in the abstract, and I also want to talk a bit about my favorite application, which is motivated by causality in this case, and that's exoplanet discovery. So what's an exoplanet transit? It means there's a star somewhere far away from here that has a planet that happens to occasionally go through the line of sight between us and that star. So that's not so often, but it's also not so rare. So if you were to travel out into space and look at our solar system, you would find that I think about 0.5% of all directions, you would potentially see an Earth transit in front of our sun. Now, you would be far away, so you would never see the Earth. The only thing you would see is a slight dip in the brightness of the sun. And the Earth is just 1% of the sun's diameter, so it's 10 to the -4 of the area. So it's a small dip. You would have to measure it very precisely to even just notice it. For this reason, people have built space telescopes to do this. And this is the Kepler Space Telescope. And this telescope has been looking at one patch of the Milky Way for several years, very precisely, and measuring light curves. And these are each thing down here is 1 pixel in the camera, measured over 3 months. So this is pixel, this is the neighboring pixel, this is the neighboring light, etc. And you see the light curves, how they get brighter. And these large trends, they are not coming from transits, they are simply from the fact that the telescope is not always looking at exactly the same location. Because the telescope has to compensate for changes in the solar radiation pressure. It orbits around the sun, so the geometry relative to our sun changes, and even the photons of the sun exert the pressure. So, and what's interesting now is so from causal point of view, first of all, this measurement that we have is caused both by the astrophysical signal, that's what we're interested in, and by the telescope. And if the telescope changes direction, then this is a non-trivial causal effect of this thing here. And it's called a systematic error. Now, interestingly, the telescope looks at several hundred thousands of stars. And if you look at some other stars, surprisingly, some of the light curves look similar to these light curves. Now, the stars are light years apart, so they don't talk to each other. There's no reason why they should be correlated. Unless there's some magic Eichenbach variable that causes both of them. But let's assume that it's not true. Astronomers don't believe that. There's a much simpler explanation, and that's the instrument. The same instrument measures both of them. And of course, that's interesting because essentially, whatever aspects in these light curves we can explain from these light curves can have nothing to do with the astrophysical signal, because we assume that the astrophysical signals are independent. So what we do basically is we run regression and try to explain these light curves in terms of these, and whatever we can explain, we remove. And you can also theoretically analyze it. So we call this method half-sibling regression, because these two variables, they share one parent, but not another parent, so they're half-siblings. And you can give some nice theoretical results that maybe I will skip. But under certain model assumptions, you can prove that up to a constant offset, you can precisely recover the random variable Q. So that's our quantity of interest, Q. So you can recover it precisely, not just in distribution, but almost surely up to a constant offset. So that's nice. And then we wrote a paper. Let me just take the counter off so I don't lose my voice, even though I don't have to shout anymore. So we wrote a paper where we use these methods. And we were lucky in a way because at some point the telescope broke. So this telescope has four devices built in to stabilize it in 3D. Normally you need 3, but they put in 4 just in case one of them gets jammed. And then, but at some point, 2 of them were jammed in the telescope, started being uncontrollable. But then someone at NASA had this great idea and said, well, we still have some fuel left, so we can use the thrusters, the remaining fuel, together with these 2 actuators to roughly stabilize the system. But then the systematic errors were much bigger. And they said, well, let's just waste the fuel and we look at some other patches that we haven't looked at yet. But the errors were much bigger, so that was good for our method. And then we ran it on that. We found a bunch of planet candidates, and most of them were then confirmed subsequently. And one of them was particularly nice because in the confirmation they also worked out all they characterized the parameters. And then people in this follow-up paper noticed one of them is in the habitable zone, which means it has the right distance to allow for liquid water. Which was already, and then the next thing that happened was someone found water vapor in the atmosphere. So it was the first time they found water vapor in a potentially habitable planet, and that was a big piece of news. I first didn't connect it, but then the astronomer David Hawk from New York, who's actually a Canadian originally, who went to school with Sam Roweis, that some of you might remember. He called me or sent me an email and said, by the way, do you know this is our planet? So there was a big discussion, is it habitable or not? And astronomers are always skeptical. So they always say, no, this is very far from habitable. And probably they're right, but then it didn't stop there. Later, they using the next space telescope, the James Webb telescope, and people discovered carbon dioxide and methane in the atmosphere. So carbon molecules, very interesting molecules that, of course, we also associate with biological process, although they can also be generated in other ways. And they found evidence to hypothesize that this planet, which is called K28b, is probably completely covered by water. With the hydrogen atmosphere above. So it's a water planet with hydrogen. You can already imagine a science fiction movie. And they came up with this notion of a Haitian world, so like ocean, but Haitian, high standing for hydrogen. And there was even speculation that they weren't sure, but there was speculation that they might have also found dimethyl sulfide, which is on Earth is something that's produced by plankton. So it's quite exciting now, and there are very violent discussions in the astronomy community whether there might be life there or not. But some people, so I recently got to know the person who runs the lab that did these detections, and he thinks that within the next 5 years or so we will know. And he thinks it's quite possible that we will have evidence for life. On this planet or on a similar planet. So this one is 111 light years away. It is quite amazing that you could even consider detecting life there. So I think it would be a big discovery. So I've talked about this too long. Maybe I should just, because we want to keep some time for discussion. So I'm going to skip the part about causal representation learning. Maybe I'll just say that we're interested in learning representation. So in a way, when I talked about causality, it was all in this heading where these symbols that you put in the nodes of the graph, they're already known. So it's kind of this classical setting. Someone gives us the variables and then we do something with them. But of course, machine learning, we like to discover the variables out of the symbols. So causal representation learning, which is one of our main interests now, is really about finding these variables. So if you look at this picture, ideally finding a representation of this picture that contains not just what we see, but also what would happen if we did certain kind of interventions. So pictures tell a story, and a story is not just what's there, but the story is a sequence. Story contains causation, counterfactuals, etc. So this, we thought about different methods for training such systems, and have different papers connecting to this. Let's see. Going to skip this. This is fine. It's some kind of model where you can, well, you skip this, and this is about compositionality. So the right causal model of a scene should be different from the standard kind of diffusion models, in that, like a standard diffusion model, I think I have an example image here. When the images look impressive, but if we look at them more closely, you see the system doesn't really understand what are individual humans. It doesn't build it in a compositional way, even though it gets better and better, but they still don't understand compositionality. And this is, I think, something that we have to improve if we want to move towards these interventional causal representations. I think there's also very interesting questions related to if you have large systems, what do they understand about causality? And maybe even the most fascinating would be whether sometimes by training something in a non-causal way, you might, as a byproduct, get certain elements of causality. And I think this could be related to compression. So we have a paper, a first paper that will probably come out soon, where we are trying to understand that. And we're also thinking a lot about like this idea of what is a representation and what would be a causal representation. And maybe I'll just give you two examples of what I think are interesting directions here. And one of them is from Leibniz and the other one is from Helmholtz. For Leibniz, as you know, he was a philosopher and mathematician, one of the inventors of calculus, even though Newton afterwards chaired a committee that decided that Newton was first. And Leibniz developed the calculus that was then later used on the continental Europe, which was the reason some mathematicians tell me that continental mathematics then took off and sort of overtook British mathematics for quite a while. Anyway, so Leibniz also came up with this notion of a homomorphism. And the example was the following. He said, suppose that the concept of living being is represented by the number 2, and the concept rational, so being endowed with reason, is represented by the number 3, then the concept of a human should be represented by 6 product with 3. And this means, so you have a structure in one domain, so the logical relationship. So if you say the logical end of living being and rational, it should map to a different structure in another space. In this case, is the structure of multiplication. So I think that's the one element. So I think representations that we form in our heads, they need to have some kind of homomorphism property connecting them to the structure in the world. Otherwise, they would be useful as models. Otherwise, we wouldn't have this illusion that the world that we think in reality is out there, that this world is somehow consistent, because of course the world is only generated in our heads. So it has to be generated in a very consistent way, otherwise it wouldn't work. And it's, oh, thank you. And it's quite fascinating to think about when there are mathematical ways of addressing this fundamental philosophical problem of why is it the case that what we come up with in our head has something to do with the world out there. So in a way, I think this is one of the deepest problems of our field, which is now leaving philosophy and entering, I hope, entering machine learning. And the second one is consistency. And this is, so Hertz, physicist, but also studying perception, he said we create internal symbols of external objects in such a way that they the images, so the consequences of the images, so of our consequences of the representations of the world in our head, the consequences that are necessary in thought, so how we imagine things should continue. Health says they have to coincide with the images of the consequences that are necessary in nature. So that means I can take an object, I look at it, I close my eyes, I move it, I open my eyes, and it's exactly in the position where I thought it would be. And this is a non-trivial consistency property, which mathematically, of course, you can write as a commutative diagram. And I think the causal representations, they have to have several of those properties. And we've been thinking about different ways of how to formalize it. Let's put it this way. So I think these causal representations that don't just include what's there, but also what would happen if you were to intervene. I think there are two big applications of this. One, of course, is AI. And it's clear that, so that's the field of causal world models, or world models for intelligent agents. And here I'd like to quote Konrad Lorenz, who was studying animal behavior, and the book that I read when I was a student, and somehow this sentence got stuck with me. He said that thinking is probably nothing but acting in the imagined space. So if you build a space that contains the notion of actions and mental simulation, etc., then this is the first step towards thinking, and thinking developed from there, you could say. And I very much subscribe to this view. So I think these models should be crucial for understanding intelligence, if intelligence involves thinking and not just pattern recognition. And the second thing is, I think they should also be very useful for modeling complex systems. So this now goes closer to scientific applications, etc. And because if you can structure a complex system in terms of causal mechanisms, and if you can come up with the right variables to write in here, so it's also a representation learning problem, then you can model these mechanisms using different tools. And you can, so we have one application where we were working on COVID vaccination data, where some of these mechanisms are modeled using epidemiological models. Some are modeled from data directly, some come from the medical literature, etc. And then you can put them together in a systematic way. And you can model a complex system even in cases where you don't have a single joint observation of all the variables at the same time. You don't need to have this. So I think that's also potentially quite powerful.
Sorry, I just think the second point is also supporting the first point, right? Like you're creating some production system that support the mental simulation based on the observational previous.
Yeah, that is true. That's true. So this thing could also play a role for intelligent
for the
agents.
simulator.
Yeah, it's very, very possible, or very likely, I would even say, that we don't use the same tools for all the components of our world model. I absolutely agree. Yeah. So So I think okay, I'm not going to go into this in details, but I think I've said something essentially about all of them. I haven't said much about this last thing: explainability, communicating cultural learning. There's an expert for explainability and causality. Here sitting in the same row, my former student Amir, who's now faculty in Waterloo. There's one thing that has bothered me for a long time, this aspect of cultural learning, which I think is very interesting. There's this fascinating book. It's called The Secret of Our Success, the book about human intelligence. And I have one quote from that. It's a book by anthropologists. No, actually, I think this is a paper. The book is just like English. And one sort of the gist of it is this quote: we accumulate information, we, humankind, accumulate information across generations. We develop tools, beliefs, and practices that are too complex for any single individual to invent during their lifetime. So we don't start from scratch. We're not like agents who start reinforcement learning when they're born as babies or supervised learning. But we have this great head start, that we have people teaching us things. We have books from which we can learn, etc. And somehow machine learning was blind on this I thought in the past for a very long time. So at some point I was thinking, what if we were able to train an AI model on humankind's cultural knowledge? And at some point it suddenly dawned to me, actually, this is exactly what we have now. So that's at least with regard to printed or visual cultural knowledge. And these are the large models that we're now dealing with. And then, of course, you could even ask the question, whether is this now a path to a human level AI, or is it just mimicking something very intelligent because it draws from this large cultural knowledge base? And I'm not going to go into detail on this, but just at the point where we have a paper, sort of an unusual, not so scientific paper with Leon Coutu, where we say, what if we, let's not discuss this in terms of science fiction, but let's discuss it in terms of a model from literature, from the writer Borges, who was one of my favorite writers when I was young, Argentinian writer. And he has this idea of this infinite library. And then, can I just take 2 more minutes? Okay. So in this infinite library, so this is now not exactly what Borges is saying, but inspired by this infinite library. So let's imagine you have a library of all possible or potentially plausible texts that a human could come up with and a human could understand them. So now you print a few words on a tape, let's call this a prompt, and you find all occurrences of these exact words in this infinite library. And then, so this will give you a bunch of books where this text occurs. Now you randomly pick one of them. In that one, you read the next words. This again gives you a plausible text because it appears in that book. You print it on the tape, you go back to step 1. So that's a language model. That's we call it a perfect language model. And you could, so first of all, there's no real notion of understanding truth of intention. It just takes these texts that are potentially plausible. So whatever understanding it has must come from biases in this library of texts. If you take a smaller than infinite library, and the second thing is that large language models that we now have in a way are actually approximations of this. So if you could build this thing, it would appear very intelligent to us, even though it's a completely stupid mechanism. And I like to compare this with this example here. There's this gentleman down here who's from New Zealand, and he was multiple times the world champion in Scrabble. And he got involved with being the world champion in Scrabble, so he decided to compete in the French Scrabble Championship. And he doesn't speak French, so he took the French Scrabble dictionary. Apparently every language has a Scrabble dictionary of which words exactly are allowed in the game, and he just learned it by heart, and he became French Scrabble champion without understanding French. So to me, this feels a bit like what the language models are currently doing, but maybe that's a little bit of provocation. And I think with that, I'll conclude, and thank you for your attention.
Okay, thank you. Oh, nice, it's working. I think we have a bit of time for questions and a discussion, so I'll open the floor. Go for it.
Thank you very much. So I'm curious your thoughts on cognitive architectures, such as like SOAR and others, because I feel like they do have some memory units that support sort of like a reinforcement learning mechanism that we can add different kinds of memory observations inside. And I feel like building causal relationships inside the memory is like crucial for higher level of reasoning capabilities and just drawing correlations based on past experience. So what's your thoughts on that? And do you think that combining with, for example, language agents will be a big boost on either reasoning capability or just actionability and those things?
Oh, I think for sure this is very promising. I think what the field has been suffering from is that on the one hand you have the causality guys, and they only do things they exactly understand, and that's to be pure. And if you deviate from that, they reject your papers. And then the other extreme is the deep learning people that are allergic to the word causality, and you start talking about it, they say, no, just show me the results. I don't want to hear anything of this because I don't understand it. So that's why it's not trivial to create something in between that will please both sides. But in a way, I think if we want to make progress towards architectures
that can do this kind of learning, then we need exactly this kind of thing of what you were saying.
Yeah, we're seeing this trend as well, so.
Yeah, I think it's changing now.
Thanks. I have a question about the notion of independent causal mechanisms and the hierarchy of random variables in the causal graph. To me, it seems that if you assume some specific causal graph on some level of hierarchy about the concepts in the world and then assume that the notion of independent causal mechanism actually works for that specific notion of concepts, then you could, in principle, define more general concepts using a combination of those random variables, those nodes in the causal graph. And if you do so, then my intuition tells me that this independent causal mechanism may not work anymore because you have some sort of dependence between different concepts if they share some common, like, lower level random variables. So first, what do you think about this observation? Second, like, do you think like the goal of field like causal representation learning is actually to figure out that specific representation in which the independent causal mechanism work or something else? Okay, thanks.
Yes, so I think maybe start with the second thing. I think that is one way to think about it. So if you want to learn causal representation, you need something that you can put in your objective function. So you would say, I want something that is intervenable. I want to have high-level variables that even permit interventions, even though they're not macroscopic, but they're aggregations of things. Or I want something that tends to, in the real world, tend to change sparsely. I want to have high-level variables which have the property that they don't always change in a distributed fashion. So I think, and I think your second question goes in this direction as to whether one can exploit something like this. And I guess I think that would be promising. And then your first question, if I understood it correctly, I think I tend to agree. So in the sense that if you had a system, if you had a microscopic causal system, where somewhere independent causal mechanisms assumptions are true, and then you aggregate variables, then for the aggregated variables, it may no longer be true. I mean, you might, it's a bit like in physics, if you come from statistical mechanics and now you aggregate, you get to thermodynamics, and it's a little bit hard to, on the statistical mechanics level, you can directly say what is the causality. But once you come to a phenomenological equation like P times V equals K times T, or what is R times T, or like the gas equation, then it's hard to say what is causing what. It's all circular. So sometimes this process of aggregation can destroy the fundamental causal structure or lead to something different. So, but maybe the two parts of the question are also connected, or maybe it is true that sometimes one could find also abstractions of systems that retain this property, so that could be interesting.
There was a work, I believe you were on 2 years, like 2022, which was about visual representation learning, not generalizing within the domain. So basically the idea that if you were to train either like representation learning method, a variety of them, or even like direct supervised method for, let's say, just synthetic data where you have fixed latents, that like compositional generalization or extrapolation or interpolation are really, really difficult to actually learn, particularly when these are outside of the support of the training distribution. And so, I mean, one question is like, do you think this is essentially a failure of the homomorphic learning properly, or maybe the entire support? And like, has your thoughts on this kind of issue changed since?
Well, I would say, I think I know the paper that you're referring to. I would say current systems don't have these properties because they also don't learn in a causally correct way. So ideally, if you were able to learn systems, if you were able to enforce that the representations that you learn have this compositional causal structure, then they should be more robust with respect to these kind of extrapolations, interpolations. So that would be also one way, one way to build a training objective, that you want to structure it such that it is robust or that it satisfies sparse mechanism shifts. So you want to express a system in terms of as products of subsystems which have this property that many of them do actually generalize. So I think it is connected to that. Based on solved.
I might, sorry, I might actually take a moment of personal privilege and ask a question that's been burning. So one of the themes that shows up in statistical learning theory is that some of our algorithms are able to naturally exploit structure in data, even if we don't tell them it's there. So one of the more famous examples, k-nearest neighbors, can behave as if it knows the underlying manifold of the data, if that's lower dimensional than the ambient space. So the question is, are there algorithms that can naturally exploit in that way the ICM hypothesis if it is present?
That's an interesting question, yes. I don't know, but I think this is a very interesting question. I mean, currently we are thinking about, it's not the same question, but kind of a similar level. We are thinking about whether transformer architectures might be able to naturally connect to this Definetti representation. So whether we somehow automatically sort of identify the latent variables that are sort of in effect in a certain context, etc. So yeah, I think that's an interesting question.
Hi, I wanted to pick up on one of the things you mentioned in an answer to a previous question, which was, right, you get this problem where you either try to submit your papers to the causal people and they say, oh, this isn't pure enough, or you submit your papers to the deep learning people and they say, oh, this isn't general enough, right? And I think I also love proposing, oh, we should do something a little bit in between, but that gets you into this very difficult space of, now you need to kind of make a bold statement about how much structure versus how much learned components do we need. And I was wondering if I could nail you a little bit more down on how would you go about to figure out if you have sufficient structure? And especially once the problem becomes as generic as language modeling or something, where even the problem is kind of ill-defined.
I think you will not manage to nail me down like a pudding that you're trying to nail on the wall. I don't know. I don't even understand exactly what is structure. So I don't know. I agree it's difficult, but I think maybe that's not a reason not to do it. Maybe it is a reason to do it. Sorry.
How would you find out if you had enough?
Not how much do you need? I don't want an answer from how much do you need. How would you be satisfied to, right? What's the thing you want to see to know, oh, this seems enough?
Okay, I would like to see systems that exhibit much stronger forms of compositional generalization that enable out-of-variable generalization. So exactly these kind of desiderata that are on my list, I think these are, from a machine learning point of view, they would be the right way of measuring whether you have causally nailed it. I think the notion of interventions in systems was the original motivation of causality, but maybe in machine learning, we should think of it much more broadly. So I agree.
Thanks.
More? Okay. Thank you, Bernhard. Join me in thanking Bernhard again. Thank you. Okay, we're good.